Hi, I'm Kevin Silmore, and today I'm going to be discussing a portion of my PhD work on understanding the behavior of 2D materials dispersed in fluids. People have long studied the behavior of polymers and flexible filaments in flows and have found a multitude of phenomena ranging from tumbling and stretching and shear flows to the famous coil stretch transition and extensional flows, all of which contribute to the interesting rheological properties of these materials. Relatively less work, though, has focused on the behavior of sheets in fluids, at least at low Reynolds number, despite the increasing prevalence of 2D materials such as graphene, transition metal, dichalcogenides, nanoplatelets, and all of the associated solution processing methods to disperse these materials in fluids. So the question we sought to address in this work is the following. What do 2D sheets do when subjected to shear flow at low Reynolds number, so either very small or very high viscosity solvent? We studied systems of thin, isotropic, athermal sheets with the following coarse-grained immersed boundary model. First, we constructed a triangulated hexagonal mesh of size L and with initial angle phi rotating out of the plane of the screen. We accounted for in-plane stretching forces, out-of-plane bending forces, as well as excluded volume interactions that prevent the sheet from unphysically self-intersecting itself. The particles that make up this coarse-grained sheet were then simulated in time with the following equation of motion that accounted for all of these energies of interaction, as well as hydrodynamic interactions that account for the motion of the fluid between the beads and how the interactions of the beads are mediated by the fluid. In addition, there was an imposed shear flow in the direction indicated on the screen and represented by this term Lx here in the equation. There are two governing dimensionless groups of this system. The first is the Furpel-von Karman number, which represents the ratio of stretching forces to bending forces. All of the sheets I'm going to talk about today exhibited very high Furpel-von Karman numbers, so bending is very soft relative to stretching modes. The second dimensionless group is something we denote as S, which relates the bending rigidity to the shear energy. And I'm going to put this in all slides. It's the dimensionless group I'm going to be focusing on the most. It's also important to note that the sheets from the hydrodynamic standpoint have no thickness. So there is a flat state in the flow vorticity plane that is stable dynamically, and I'll be mentioning that later. One of the harder parts of this model is calculating the mobility matrix at every time step. Like electrostatic systems, hydrodynamic interactions are very long range, detaining like 1 over the radius between different particles, meaning the interactions can't be cut off at a certain distance. The Swan Group has developed specialized GPU-accelerated algorithms to calculate all of these pairwise hydrodynamic interactions efficiently on graphics processing units. And the results I'm presenting here today, I should mention, required thousands of GPU hours in total. On the analytical side of things, we know that the solution for spheres moving around in Stokes flow. We also know the solution of how rigid ellipsoids behave in Stokes shear flow due to work from Jeffrey in the early 1920s. Here's the Jeffreys equation for infinitely thin rigid disks in shear flow, where omega is the vorticity tensor and E is the strain rate tensor. And we can see in this plot I'm showing here of the orientation angle versus time, even for very flexible sheets over a wide range of S values, dimensionless bending rigidity, the orientation of these sheets is still predicted very well by the associated Jeffrey orbit for a flat, rigid particle. And this is despite the fact that these sheets buckle in time. Now, what do I mean by buckling? Here I'm showing snapshots of 30 different sheets in the middle of their trajectories, and we can see that these sheets buckle very, very differently as a function of S, which is increasing from the top left to the bottom right. So the softest sheet relative to the shear flow is at the top left, and the stiffest is the bottom right. In time, these sheets look like the following. So here are 3 sheets, S increasing from left to right, so softest to stiffest. You can see this sheet on the left, the softest one, buckles quite considerably, whereas the one on the right remains relatively flat the entire time through its trajectory. And I'll play that again. And you can see all of them eventually approach this stable flat state that I mentioned for long times. In order to explain such buckling, we derived a 1D quasi-static model of elasticity governing small deviations from flatness. And I say quasi-static in the sense that the stresses we assume to be a function of the orientation angle in time theta, in turn governed independently by a Jeffrey orbit. I'm glossing over a lot of the details, but in this model, we've accounted for the changing width of the hexagonal sheet, out-of-plane stresses, in-plane stresses, as well as boundary conditions that represent symmetry of the sheet across the center streamline of the shear flow, as well as free ends, so no forces or no moments at the ends of this sheet. Similar to classical Euler buckling of beams, so when you compress a beam, it buckles out, one can write down a generalized eigenvalue problem to solve for the buckling transitions of the sheet, where the operators on the left and right-hand side, A and B, correspond to the left and right-hand sides of this differential equation here, but discretized via a basis expansion in polynomials. Here I'm showing the bending energy over time for many different values of S. So each vertical slice here represents a different trajectory of a sheet. So soft on the left to stiffest sheet on the right relative to the shear flow over time on the y-axis, and the color represents the bending energy. On top of this graph, I can overlay the predicted transitions from the model on the previous slide at the angle of maximum in-plane stress. And I've put down points A, B, C, and D between these different buckling transitions. And we can look at snapshots at these points. You can see A, B, and C look pretty similar. D, the softest sheet, you can see buckled, but we can really see that these sheets lie in different buckling regimes when looking at the mean curvature over the intrinsic coordinates. So we can see that the mode number increases as the sheets get softer, and this very much affirms the validity of the simple 1D quasi-static model that we propose. So everything I've talked about so far were for sheets initially oriented in the flow vorticity plane, but different behavior can result for different initial orientations. So here again, I'm showing 3 different sheets with increasing S values from left to right. So softest on the left to stiffest on the right. And we can see the softest sheet starts to tumble and crumple and continuously tumbles, in fact. The right one, the stiffest sheet, remains flat for its entire trajectory, really tracking the Jeffrey orbit very closely. The middle sheet of intermediate S value initially tumbles, but you can see right now is settling down toward the stable flat state for long times. One can quantify this behavior by looking at the mean orientation over time. So to do this, we calculated something known as the Frechet mean, which is defined as the orientation that minimizes the distance on the unit sphere to all of the little unit normals across the surface of the sheet. So this is a nice way to average all of the little individual orientations across the sheet. In looking at the mean orientation over time, we can classify trajectories into those that are incredibly close to Jeffrey orbits in black dots here, those that initially tumble but eventually reach the stable flat state after long times, shown in orange, and those that continuously tumble and crumple and never stop tumbling for as long as we observe them in red. And so this state diagram, again, is a function of S, and on the y-axis, it's a function of the initial orientation. The mean orientations for some of the points in the state diagram look like the following. So here I'm showing the mean orientation over time, where time is represented in color. For a quasi-Jeffrey orbit, as we denote it, you can see nothing too exciting happens. The mean orientation moves a little bit around in time and settles toward the stable flat state at the pole of the sphere. For a sheet that initially tumbles, we can see for a time up to about 200, the orientation is changing, but eventually settles down to the stable flat state. But exciting things happen for the continuously tumbling, very soft sheets. One can see that the orientation continues to change over the entire time we observe it. In order to quantify crumpling, we looked at the eigenvalues of the covariance matrix of all the little unit normals, their spread about the mean orientation. So here I'm plotting the sum and the differences of these eigenvalues of this covariance matrix over time for a few different values of S and 2 initial orientations of 53 degrees and 54 degrees. The sum of the eigenvalues represents the overall degree of crumpling, and the difference represents the degree of anisotropy of crumpling. To give you a better physical picture, 2 eigenvalues that are positive represent crumpling relatively uniformly. The unit normals are scattered about the mean orientation in every different direction uniformly. If both eigenvalues are 0, that represents a flat sheet. There's no spread of the unit normals about the mean orientation. And if one eigenvalue is positive and one is close to 0, this represents a sheet that's folding like a potato chip kind of, it's creasing anisotropically. So going back to the graphs at the top, we can see that the softer sheets, shown in gray, crumple more, and they do so more uniformly than the stiffer sheets, one shown in red, which exhibits a higher degree of crease-like folding and eventually settles down to the stable flat state by a time of 1,000. We can also look at the mean orientation for the softest sheet, so the red trace, and we can see that small differences in initial orientation, just 1 degree difference between 53 and 54 degrees, can lead to vastly different trajectories, which you can qualitatively see in these plots on the spheres here. Now, of course, small perturbations of initial conditions that lead to vastly different trajectories, that's a hallmark of chaos. And we have found and we see that crumpling goes hand in hand with such deterministic chaos in these complicated flexible sheet systems. So everything I've talked about, all the previous data I discussed, was for athermal sheets. Introducing thermal fluctuations into the system causes sheets to stochastically flip and change conformation over time. So here I'm showing a lot of distributions, violin plots, of the times between these stochastic flips as a function of temperature, going from low temperature in the top left to high temperature in the bottom right, as well as a function of S again. So soft sheet is low S, stiff sheet is a high S relative to the shear strength. We can see that in general, the time between flips decreases as temperature increases and sheets fluctuate more and more wildly, which makes sense. We can also see that the transition to chaotic behavior, which I mentioned before for the athermal sheet system, is apparent here. As S decreases and the sheets become softer, they crumple and tumble very rapidly. And this is represented by the small flipping times at the left of each of these plots. These stochastic conformational changes over time can greatly affect bulk rheological properties of dilute suspensions of 2D materials, such as the viscosity and the first normal stress difference, both of which I've calculated and I'm showing here. In case you haven't heard of the first normal stress difference, it's responsible for something known as the Weissenberg effect, which causes certain materials to somewhat bizarrely climb up rotating rods, counter to what you might expect with water. But looking at the viscosity plot, here I'm plotting the viscosity contribution as a function of inverse S, so it goes like shear rate. As shear rate increases, we can see that viscosity goes down. So in that regime, dilute suspensions of 2D materials are shear thinning like ketchup. But if you shear these sheets hard enough, they crumple and tumble and the viscosity increases again. So they shear thicken like cornstarch and water. Additionally, we can see that there are non-zero normal stress differences at low shear rates, which means a dilute suspension of sheets could exhibit the Weissenberg effect. Skipping over many of the details, I'll also mention that one can write down a physical model accounting for diffusive and advective modes of motion in order to predict universal scaling laws for flipping statistics as well as the viscosity. And the data in the applicable regimes of S and temperature seem to collapse well onto master curves, which I've drawn here. We believe these scaling laws will be quite useful for predicting and understanding the bulk rheological properties of suspensions of 2D nanomaterials. And as a shameless plug for the CSGF program, I'll also mention that without high performance computing, it would not have been possible at all to test such theories and ideas. So computational models can really help us understand real systems that are hard to probe experimentally or otherwise. With that, I'd like to acknowledge conversations with fellow members of the Swan and Strana groups, as well as other mentors I've had at MIT, such as Pat Doyle, Gareth McKinley, and Nikta Fakhri, who have greatly helped inform this work. And last but not least, I'd like to thank the CSGF program. It's been such a wonderful experience to be a part of this program over the past 4 years. And I am just so thankful for all of the support and to be part of such a wonderful community. So I'll leave this conclusion slide up and I'll be happy to take any questions. Thanks.